Okay, this is the video tutorial for lesson 15.2. This is partial fractions, part 1. There's actually going to be 4 lessons on partial fractions. And in this one, the objective is to be able to write fractions with linear factors. And we're talking specifically about denominators having linear factors. Now, as this is our first lesson, here was the warm-up that went with it. If you want to try pausing the video and trying this one, you certainly can. And we're going to skip straight to the answer here. Now, what we notice about this question, or perhaps what we don't notice about this question initially, is most people would normally just go ahead and simplify this and then work out what they have. Now, what's actually useful for this question is to break it into smaller pieces. Now, one thing we certainly notice about this question is that we can see that the denominators are just each term multiplied by 1 more. And noticing that this 2 here starts here. So this is a 3 and a 3. So they're basically each term is increasing by 1, but the number you're multiplying is 1 bigger than the first number. So in general, each term you can write as 1 over n times n plus 1. Now, if we start breaking this down, and actually splitting this up. So notice we have 2 terms here. So we want to try and split this up into 2 fractions, something over n and something over n plus 1. Now, here's the steps that went ahead to go ahead and do that. And then what we notice is we end up with this. Now, this is more useful for us rather than this to try and see if we can spot a pattern. So notice what happens then if we use this just for the numeric question to begin with. So that first term, the 1 over 1 times 2, we can rewrite like this. The 1 over 2 times 3, we can rewrite like this, and so on all the way to the end here. Noticing here in the middle, if we regroup, then we have terms that actually will cancel out. Negative 1/2 plus 1/2 will cancel. Negative 1/3 plus 1/3 will cancel. And all we're going to finally get left over with is this first term and this last term. So what we notice for this particular question is the 1 up to 100. We can just write it as 1 minus 1 over 100, which is 99 over 100, which is much quicker than working out all 100 terms and then finding out what their sum and difference is. So partial fractions is a method of breaking down complex fractions into something that involves products into sums or simpler fractions. And then hopefully like this, we can actually do some operations. Specifically for calculus, we want to do this because integrating or differentiating something that is a complicated fraction might be really difficult. If we can split it into smaller fractions, then hopefully individually they should be easier to work out. So specifically in this lesson, we're going to be looking at being able to split rational functions into their partial fractions. But for this question only, just ones that have those linear factors as part of their denominator. So this is an example of one of those questions. So the main thing we have to look at is the denominator, and we have to see if there is something that we can actually do with that. So certainly being able to factor is really important for a question like this, x plus 3 and x minus 2, which you can see are both linear factors. So what are we trying to do? Well, we're trying to split it up into 2 separate fractions, something over x plus 3, something over x minus 2. The thing is, we don't know what these 2 terms are. What we do know as mathematicians is that when we have linear factors, that all we're going to have is constant terms here. So there'll just be something like a 2 or a 3. It won't be anything like 3x or 2 minus 5x. It'll just be a constant. So we go ahead and we set up the question like this. Now, we've gone straight for a more complicated question. We've immediately gone for an integration question here. In general, it could just be just what is this in partial fractions? But to save time, we're going to go ahead and do one big question so you can see how everything would work together. And then what we do is we just do our basic rules of fractions like you would have practiced in lesson 15.1. Make a common denominator. So although we're trying to split this into partial fractions as 2 separate fractions, we actually begin by putting it back together into a single fraction, and then we can start making some comparisons. So we multiply both sides by x minus 2 here. We multiply both sides by x plus 3 here. And then as we have a common denominator, we can now add this together and just make a single fraction. Now, the reason this is helpful then is notice the denominators are the same. And if these 2 fractions are the same, then we can also say that the numerators are going to be the same as well. So in other words, this would equal this. And then there's 2 different methods that we could use to actually go ahead and solve this. So let's look at the first one to begin with. So there was the original question, and that's where the point that we're up to right now. Now, certainly when we have parentheses, we know that we can distribute, so we can go ahead and do that. And we could try and collect like terms together here. So I got my AX and my BX, so I could take those together and factor out an X. Negative 2a plus 3b, that's just my constant, so I could put those together as well. And then what I can say is, well, if these things are equal, then the number of x's must equal the number of x's. So a plus b must equal 7. And what we call this is comparing coefficients. And specifically, we're comparing coefficients of x for this question. Now, normally what I would actually do is I would actually do that straight from here. I would kind of just distribute in my head and see what gives me an x. So I can see ax here, and I can see bx. So I would literally just write a plus b equals 7 straight away. And I probably wouldn't even do these 2 lines here. And similarly for the numbers, I can see a times negative 2 is negative 2a, b times 3 is 3b. So negative 2a plus 3b equals 11. And you can see that's the same thing that we have here. As we have 2 unknowns, we of course need 2 equations. This would just be a system. You can solve it whichever way you prefer. You can do it by substitution for solving one of these equations, or you can do it by elimination. And I'm going to use trivially here. A is 2 and B is 5. And you can certainly go and work that out if you wish. So what we know then is, going back to the original question, we had originally a over x plus 3. So now I can say it's 2 over x plus 3. It was originally b over x minus 2. So I can say it's 5 over x minus 2. And as I'm integrating here, sometimes it's useful to bring that constant term just to the front. Now, it is specifically for this question because I'm kind of using this rule over here, which seems to be hidden just a little bit. There we go. Let me bring it up. A little bit of a joke here. But when we have our fractions, one of the things that we're looking for is, if the top is the differential of the bottom, then we can use the ln function as our integral. So let me move that out of the way. So certainly the differential of x plus 3 is 1, which is a good reason for writing it as 2 times 1. And same for this one here. The differential of x minus 2 is 1. So I want to write this as 5 times 1. So now the top is indeed the differential of the bottom. And then you can do that just as we said. It would be 2 times the ln of the bottom, put it in absolute value so we don't get any negatives, plus 5 times ln of the bottom here, and plus c. Of course, you might have limits for these questions as well, but not specifically for this one. Now, the method I just showed you is important for probably questions for future lessons. There is an easier method that you should always try and do first, but it won't always work for every question, but it will for this lesson specifically. So when you get to here, another way you can try this, so this is method 2, is you can try and create zeros, and that will also eliminate one of the variables. So what we're looking for is key values that would make one of the sets of parentheses 0. So clearly, if I make x equals 2, I've eliminated a here because I got a times 0, which is just 0. And then as we plug in here, 2 plus 3 is 5. Plug 2 into this side, I get 25, and then you can solve for b. You'll notice this is far less steps. And if we can ever do this, this is always the method we want to try first. And to make the second set of parentheses 0, you would substitute in negative 3. So do the same here. Negative 3 minus 2 is negative 5, a. This is 0. And then substituting into the right-hand side gives negative 10. So that also gives you a equals 2. And then once you have that integral, you can just go ahead and integrate it just like we did previously. So this is by far the preferred method. If we have the choice, we want to try and create zeros. It's just that we can't always do that. Sometimes we don't have linear factors. And sometimes, as you'll see in next lesson, that won't be sufficient to find all of the variables as well. So I would recommend for the questions, try and focus on this second method that was shown, but just be aware of that first method because it is important, specifically starting from lesson 15.3, you will always need to use that. That's the end for this video. There are additional videos on YouTube that actually answer some of the questions that are part of the assignment, so go use those as well if you need additional help.